Today we're switching gears. Instead of solving quadratic equations, today we'll be finding the intercepts of quadratic functions. So a function is a special type of relationship between two variables. Usually we're talking about x and y. And I'm saying special because every input, that is every x value, has to have a unique output or y value. And so instead of solving equations today, our ultimate goal will be leading up towards graphing these relationships, these functions. And part of graphing is knowing where the intercepts are, right? And an intercept is a point that crosses or intersects an axis. So either the x-axis or the y-axis. Today we'll be focusing on quadratic functions, and we know that quadratic functions are functions in the form ax squared plus bx plus c. Being that they're functions, these are now going to be equal to our output variable y, or f of x. So let's get started with our guiding idea. If we're writing down the coordinate pairs of the intercepts, let's take a look. This would be -2, 0 and 1, 2, 3, 0. This function, I'm intentionally using functions that you may or may not be familiar with because we want to find out a certain principle. That's regardless of the type of function. Oh, this would be halfway between 1/2 and 1, so that would be 3/4 or 0.75. Okay, let's go back and look at these y-intercepts. This one looks to be at about 0, -6. This is an x and a y-intercept. Interesting. What do you notice about the intercepts of these functions? Well, I notice that an x-intercept, whether it's for a quadratic function like an a, or b is a sinusoidal function, we'll talk about those in Unit 7. C is a polynomial function, we'll look at those in the next unit, but it doesn't really matter. In all of these cases, x-intercepts always have the y value 0. That's why they're crossing the x-axis, is because y is 0, and y-intercepts always have the x value 0. So let's apply that idea to our first example. To find the intercepts of the function, first we'll find x-intercepts. And we know that x-intercepts always have the y value 0. So we'll start by substituting 0 for y. Now this is a quadratic equation that we've been solving for the full unit. So we can think of two numbers that multiply to 10, add up to -11. That would be -10 and -1. We can solve this equation by factoring. It's always a little bit faster than using the quadratic formula, so I try to factor if I can. Notice I'm getting x minus 1 for that second set of parentheses, the second factor, because of the hidden 1 there. I set each factor equal to 0 because essentially I have something times something else is 0. We know the only way to multiply two things to get 0 is if one of them is 0. So either x is 10 or x is 1. That gives me two x-intercepts, 10, 0, and 1, 0. Now, intercepts implies find the x and the y-intercept. So let's also find the y-intercept. We know from our guiding idea that anytime you have a y-intercept, the x value is 0. So here we're going to substitute 0 in for x. We get y is 0 minus 0 plus 10, so y is 10. So we have the coordinate pair 0, 10. Okay, let's take a look at a second example. Name the x and y intercepts of this function. Again, x-intercepts, we know that the y value is 0. Let's substitute and see where that takes us. Oh, how convenient. This is already factored. So we set each factor equal to 0. Again, this is one factor. It's x or x minus 0. And if we're going to multiply x by something, in this case 9x minus 8, one of these two guys has to be 0. So I have 0, 0, and 8/9 0 are my two x-intercepts. To find the y-intercept, we know that x is 0, so we're going to substitute. 0 times anything is 0. Oh, well, that makes sense. We had already found that the function intersects the origin. Since x is 0, it counts as a y-intercept. Since y is 0, the origin is also an x-intercept. So these are all the intercepts of the function. Okay, let's take a look at one final example. Where does this function intersect the x and y axes? That's saying, what are the x-intercepts and y-intercepts? So again, to find x-intercepts, we set y equal to 0. We haven't been solving equations in this form much, so let's walk this through carefully. My order of operations, PEMDAS, tells me that before distributing or multiplying the two, I should take care of the exponents. So let's deal with that x minus 3 squared, or x minus 3 times x minus 3 first. So we have 0 equals 2 times the quantity, x squared minus 6x plus 9. Now that we've done exponents, now we can do multiplication. Distribute this 2. Here we have a quadratic equation where that leading coefficient is not 1. I don't know how to factor when that leading coefficient is not 1, so let's use the quadratic formula. Writing it out every time helps me remember. The opposite of negative 12, so that would be positive 12. All over 2a, not just the square root. Let's deal with what's inside the parentheses first. Again, PEMDAS tells us we have to deal with exponents. Oops. And multiplication. I'm going to leave that subtraction sign right where it is. I get 12 plus or minus the square root of 144 minus 4 times 2 times 19 would give me, let's see, some number. Sorry, I forgot to, 19 times 8, 72. 8 plus 7 would be 15, 152, all over 4. So if x equals 12 plus or minus the square root of negative 8 all over 4. Now, we know the square root of negative 8. This right here is an imaginary number, right? It's the square root of 8i. An imaginary number means there won't actually be any x-intercepts. So we can stop right here and conclude there are no x-intercepts. Doesn't mean there's not a y-intercept, so let's try to find that. Oops. Again, we're finding y-intercepts by setting x equal to 0. So we have g of 0 is 2 times the quantity 0 minus 3 squared plus 1. Order of operations, deal with what's in the parentheses first, then exponents, then multiply. So we have the y-intercept 0, 19.